In the previous lecture, we looked at a public key encryption system that's built from RSA or more generally from trapdoor functions. In this lecture, we're going to look at public key encryption schemes that are built from the Diffie-Hellman protocol. So first, recall that a public key encryption system is made up of three algorithms. There's a key generation algorithm that I'll denote by gen that basically generates a public key and a secret key. And then there are two algorithms, E and D, that encrypt and decrypt. And the point is the encryption algorithm encrypts using the public key, and the decryption algorithm decrypts using the secret key. The physical world analogy for public key encryption is a locked box where anyone can put a message inside the box and then lock the box. That corresponds to the public key. And then no one can open this box except the person who has the secret key that has the key can put it in the lock, unlock the box, and recover the message in the box. Now, in the previous lecture, we looked at a number of applications for public key encryption. In particular, we looked at the key exchange application. And in fact, this is how public key encryption is used in SSL, where the server sends its public key to the browser chooses a secret, and then encrypts the secret using the server's public key, sends it back to the server decrypts, and now both the browser and the server have a common secret that they can then use to encrypt data going back and forth between them. So in the interactive settings, such as in a networking protocol, public key encryption would primarily be used for setting up a shared symmetric key which the two parties can then use to exchange information. However, there are many settings where interaction is simply not possible, and then public key encryption is directly used to encrypt messages. One example of this is secure email. The email system in some sense is designed to be non-interactive in the sense that the sender sends an email, the email travels from relay to relay to relay until it finally arrives at the destination, and the destination should be able to decrypt without interacting with the sender at that point. That can be done basically by the sender encrypting the message using the recipient's public key. The ciphertext would travel along the SMTP chain until it reaches the recipient. The recipient would use a secret key and recover the original sent message. However, there are many other cases where interaction is not possible, and I want to show you two such cases. The first example is file systems. And in fact, public key encryption is a good way to manage file sharing in an encrypted file system. So let me show you what I mean by that. So imagine we have our friend Bob here who wants to store an encrypted file on some storage server. So he'll go ahead and write the encrypted file to the storage server. What he actually writes on the server is basically the following. He will generate a random file encryption key, we'll call it K sub f, and then he will use a symmetric encryption system to encrypt the file using the key K sub f. Then he'll encrypt the key K sub f using his own public key, so public key of Bob. This will give Bob access to the file at a later time, right? Using his secret key, Bob can decrypt this header, recover K sub f, then he'll decrypt the actual encrypted file and recover the plaintext file. So decryption will work in two steps. However, if Bob now wants to also give access to Alice to this file, what he'll do is he'll go ahead and in addition, he'll also include in the file header an encryption of K sub f under Alice's public key. Okay, so notice that there was no interaction here. All Bob knows is Alice's public key, and yet he was able to make the file accessible to Alice at a later time. So now Bob disappears, and then Alice comes and accesses the disk at a later time. She'll read the ciphertext, decrypt her part of the header, recover KF, and then she can decrypt the symmetrically encrypted file and recover the actual file contents. Okay, so you can see that without any interaction, Bob was able to write to the file system and enable Alice to access the file as well. Again, at the time that Alice was reading the file, there's no interaction with Bob because maybe Bob is already inaccessible, and yet Alice can still read the file and recover it by herself. So another example of a non-interactive application of public key encryption is what's called key escrow. Now, key escrow may actually sound like a bad thing, but in fact, it's a mandatory feature in corporate environments. So the idea here is this. So imagine Bob writes data to a disk, and then later Bob becomes inaccessible. Maybe Bob is fired, maybe Bob is out sick, and somehow the company needs to have access to Bob's files. So having Bob be the only one able to decrypt these files is simply unacceptable in a corporate settings. The corporation might need access to those files. So the question is what to do, and the answer is to introduce this entity called a key escrow service. And the way the system then would work is as follows. Basically, when Bob writes his file to disk, his system, as it's writing the file to this shared storage medium, what it would do, of course, as before, it would encrypt the file using the file encryption key KF. It would encrypt KF using Bob's public key, but it would also encrypt KF using an escrow service. So here, the escrow service is completely offline. We never talk to it unless we actually need its services. As Bob is writing the file, all he does is he simply writes the encryption of KF under the escrow authority's public key into the file header. Now later Bob disappears, and now the company needs to recover Bob's file. What does it do? Well, at this point it would contact the escrow service. The escrow service would read this part of the header, use its secret key to decrypt the header and recover KF, and then use KF to decrypt the actual file. Okay, so in this way, again, you notice that the escrow service was completely offline. There was no interaction with the escrow service until the point at which the escrow services were actually needed. And again, you can see that this is a very clean and elegant application of public key encryption. So as I said in the previous lecture, we saw constructions for public key encryption based on trapdoor functions. In particular, we looked at RSA. We looked at the generic construction we call the ISO standard. We looked at constructions like OEP+, and so on and so forth. In this lecture, we're going to look at public key constructions from the Diffie-Hellman protocol. This is another family of public key systems, and I'm going to show you how they work. These public key systems are generally called ElGamal public key encryption schemes. Taher ElGamal was actually Marty Hellman's student. He came up with this ElGamal encryption system as part of his PhD thesis. And in fact, ElGamal encryption, for historical reasons, is used in an email encryption system called GPG, the GNU Privacy Guard. As usual, when we construct public key encryption systems, our goal is to build systems that have chosen ciphertext security so that they are secure both against eavesdropping and tampering attacks. So before I show you the ElGamal system, let's do a very brief review of the Diffie-Hellman protocol. So in my description here, I'm going to abstract it a little bit from the version that we saw last week. And in fact, I'm just going to use the concept of a finite cyclic group. In fact, we have an arbitrary finite cyclic group. For example, it could be the group ZP star, but it could also be the points of an elliptic curve. And as I mentioned, there are some benefits to doing Diffie-Hellman over an elliptic curve. But for simplicity, I'm just going to refer to G as an abstract finite cyclic group. But in your heads, you should be thinking G is the group ZP star. And let's suppose that the group has order n for some integer n. Now we're going to fix a generator G of this group. And all this means is basically, if you look at the successive powers of G, then basically you get all the elements in the group G. You notice that because the group has order n, we know that G to the power of n is equal to 1. And therefore, there's no reason to go beyond the n minus first power of G. G to the n is equal to 1, so that we just wrap around. Okay, so we have this cyclic group G. We have this generator whose powers give us all the elements of G. And now let me remind you how the Diffie-Hellman protocol works. Basically, what Alice does is she chooses a random A. She computes G to the A and sends that over to Bob. Bob chooses a random B, and let's see who remembers. What does Bob send over to Alice? So Bob sends over to Alice G to the B, and of course I should remind you that both G to the A and G to the B are just elements in this group G. And now they can derive a shared secret. If you remember, the shared secret is G to the AB, and these equalities here show that both sides can actually compute the shared secret given the values at their disposal. So Alice, for example, has B and she has A, and so raising B to the power of A gives her the shared secret. The attacker, of course, the poor attacker, he gets to see A and B, and his goal is now, of course, he also gets to see the generator G, and his goal now is to compute G to the AB, but we said that this is believed to be a hard problem given G, G to the A, and G to the B. In a group like ZP star, computing G to the AB is difficult. So now let's see how to convert the Diffie-Hellman protocol into an actual public key system. And as I said, this was a brilliant idea due to Taher ElGamal. So as before, we're going to fix our cyclic group G and a generator little g inside of G. Now here I wrote the Diffie-Hellman protocol again, except now we're going to assume that these guys are separated in time. So these two steps don't have to occur simultaneously. They could actually take place at quite different times. The first step of the Diffie-Hellman protocol is what we're going to view as key generation. That is, the public key is going to be this capital A, and the secret key is simply going to be the little a. So you notice, of course, that extracting the secret key from the public key, namely extracting little a from capital A is a discrete log problem, so that recovering a secret key is actually difficult. Okay, so this gives us our public key. So now at a later time, Bob wants to encrypt a message to Alice, encrypted using her public key. So how does Bob encrypt? Well, what he's going to do is he's going to compute his contribution to the Diffie-Hellman protocol. Namely, he's going to send over G to the little b. Of course, he's going to choose this little b at random. And now he's going to compute by himself the shared secret. So he's going to compute by himself G to the AB. From this G to the AB, he's going to derive a symmetric key for a symmetric encryption system. And then he's going to encrypt the message M using the symmetric key that he just derived. And that's the pair that he's going to send. So he's going to send over his contribution to the Diffie-Hellman protocol plus the symmetric encryption of the message M that he wants to send over to Alice. Okay, so you can see basically we are doing the exact same thing as we would do in the Diffie-Hellman protocol, except now where Bob directly, immediately is using his Diffie-Hellman secret to encrypt the message that he wants to send over to Alice. Now what does Alice do to decrypt? Basically, she's going to also compute the Diffie-Hellman secret. Remember, now she just received Bob's contribution to the Diffie-Hellman protocol, and she has her secret key A, so she can compute also the Diffie-Hellman secret, namely G to the AB, from which she's going to derive the symmetric encryption key K, and then she's going to decrypt the message to recover the actual plaintext. Okay, so that's the intuition for how we convert the Diffie-Hellman protocol into a public key system. By the way, this was kind of an interesting development at the time that it came out, partially because you notice this is a randomized encryption scheme. So every time Bob encrypts a message, it's required that he choose a new random B and encrypt the message using this new random B. So let's see the ElGamal system actually in more detail. So now actually let's view it as an actual public key encryption system, namely algorithm Gen, algorithm E, and algorithm D. So as usual, we're going to fix our finite cyclic group of order n. Another ingredient that we're going to need is a symmetric encryption system. So I'm going to refer to it as E sub s and D sub s. These are the encryption and decryption algorithms of a symmetric encryption system that happens to provide authenticated encryption. And the key space for this system is capital K. And then we're also going to need a hash function that maps pairs of elements in the group, namely elements in G squared, into the key space. Now here's how the public key encryption system works. So I have to describe three algorithms. Algorithm that generates the public key and the secret key, and then the encryption and decryption algorithms. So the key generation algorithm works as follows. All we do is basically build up Alice's contribution to the Diffie-Hellman protocol. What we're going to do is we're going to choose a random generator G and G, and then we're going to choose a random exponent A. The secret key is going to be A, and then the public key is going to be the generator G and Alice's contribution to the Diffie-Hellman protocol. The reason, by the way, we don't use a fixed generator is because it allows us to somewhat use a weaker assumption in proving security, and so it's actually better to choose a random generator every time. It's easy enough to choose a random generator. All we do is we take the generator that we started with, and then we raise it to some power that's relatively prime to n. And that will give us another generator, a random generator of the group capital G. Okay, so you can see here that again, public key is simply Alice's contribution to the Diffie-Hellman protocol, and the secret key is the random A that she chose. Now, how do we encrypt and decrypt? Well, when Bob wants to encrypt a message, he's going to use the public key. Remember, it consists of G and H, and here he wants to encrypt a message M. So here's what he's going to do. So he's going to choose his contribution to the Diffie-Hellman protocol. So this is the secret B that he would normally choose in Diffie-Hellman. And now he's going to compute G to the B, which is actually his message that gets sent to Alice in the Diffie-Hellman protocol. He's going to compute the Diffie-Hellman secret. That's H to the B. If you remember, H was G to the A. Therefore, this value here is really G to the AB. That's the Diffie-Hellman secret. That's the one thing that the attacker doesn't actually know. Next, he's going to compute a symmetric key by basically hashing this pair U comma V. So U, of course, is something that the attacker is going to know because that's going to be sent as part of the ciphertext. But V, the attacker isn't going to know. Again, for the proof of security, actually, it helps to hash both U and V. And so we hash both of them together. Although, strictly speaking, we just needed to hash V because V is the only value that the attacker doesn't know. The attacker already knows U because that's going to be part of the data that's sent on the network. So anyhow, so Bob derives this symmetric key K by hashing U and V. Then he goes ahead and encrypts the message using the symmetric key K. And finally, he outputs his contribution to the Diffie-Hellman protocol, the value U, and then the symmetric ciphertext that directly encrypts the message M. That's it. So the ciphertext consists of these two parts, and that's the thing that gets sent over the network. Let's see how does Alice decrypt now. So she's going to use her secret key A to decrypt, and she receives here Bob's contribution to the Diffie-Hellman protocol, plus the symmetric encryption of the message that Bob sent. What she'll do is she'll compute herself the Diffie-Hellman secret. If you remember, U to the A is simply G to the B to the A, which is G to the AB. So here, Alice computed the Diffie-Hellman secret. And now let me ask you, how does she derive the symmetric key K, given the Diffie-Hellman secret G to the AB and the ciphertext that she was given? Well, what she'll do is simply, again, now she has U from the ciphertext, and she has V because she just computed it herself. So now she can rederive the symmetric encryption key by hashing U and V together to get the symmetric encryption key, and then she just decrypts the ciphertext to get the actual plaintext. Okay, so that's it. That's the whole encryption and decryption algorithm. In a picture, the way the ciphertext would look is also as kind of what we saw in the last lecture. Basically, there would be a short header that contains U, which, as you recall, is G to the B. And then the rest of the ciphertext would be the encryption of the message that's being sent under the symmetric key K. And then to decrypt, Alice would use this header to derive the Diffie-Hellman secret, from which she will derive K, and then decrypt the body to get the original plaintext. By the way, I should note that the way I describe the system here is actually not how ElGamal described it originally. This is in some sense a modern view of ElGamal encryption, but it's pretty much equivalent to how ElGamal viewed it. So now let's look at the performance of ElGamal. So here what I wrote is the kind of the time-intensive steps of ElGamal encryption. Namely, during encryption there are these two exponentiations in the group G. Exponentiation, remember, is a cubic time algorithm using the repeated squaring algorithm, and as a result it's fairly time-intensive. And when I say time-intensive, I mean that on a modern processor it would take a few milliseconds to compute these exponentiations. And during decryption, basically the decryptor computes one exponentiation, namely U to the A. This is the bottleneck during decryption. Okay, so you would think that encryption actually takes twice as long as decryption, because encryption requires two exponentiations, whereas decryption requires only one. It turns out that's not entirely accurate, because you notice that the exponentiation during decryption is done to a variable basis, namely U changes every time, whereas during encryption, the basis is fixed. G and H are derived from the public key and are fixed forever. So in fact, it turns out if you want to do exponentiation to a fixed basis, you can do a lot of pre-computation. In particular, you can do all the squaring steps in the repeated squaring algorithm offline. So here what you would do is you would compute all powers of 2 of G. So you would compute G, G squared, G to the 4th, G to the 8th, G to the 16th, G to the 32, and so on and so forth. These are all the squaring steps of the repeated squaring algorithm you would do offline. The same thing for H, and then when it comes time to actually do the real exponentiation, all you need to do is just do the multiplications to accumulate these powers of 2 into the exponent b that you're trying to compute. So if you think about it, this can actually speed up exponentiation by a factor of 3. In fact, it would speed up it even more if you allow me to store even larger tables. This is called a windowed exponentiation. But regardless, if you allow the encryptor to store large tables that are derived from the public key, then in fact encryption is not going to be slower than decryption. In fact, encryption will be faster than decryption. But again, this requires the encryptor to pre-compute these large tables and store them around. So if all the encryptor is doing is just constantly encrypting to a single recipient, that could be done actually fairly fast using these pre-computed tables. If the encryptor for every message is encrypting to a different recipient, for example, if every time you send an email to a different recipient, then in fact the encryption will be twice as slow as decryption. So this is a good trick to keep in mind. In fact, most crypto libraries don't do this. And so if you see that you're always encrypting to the same public key, and for some reason your encryption process takes a lot of time, is a bottleneck for you, keep in mind that you can actually really speed things up using pre-computation. Of course, if encryption is a bottleneck for you, you might as well be using RSA, where in RSA encryption is really fast. Okay, so that's the end of our description of ElGamal encryption. And now the next question, of course, is why is the system secure? In particular, can we prove that it's chosen ciphertext secure? And more importantly, kind of under what assumptions can we prove that the system is chosen ciphertext secure? And so we're going to discuss that in the next segment.